Good afternoon or good morning, according to where in the world you are right now. I am Rita Nogherotto, and today I have the ambitious task of describing the parameterizations of Regcm. I will try to highlight the differences between different schemes we use for tuning our model, to understand better what they do and to help us in interpreting the results we obtain. So let's start from the beginning. Let's say we have installed the model, successfully compiled it, and finally made sure the model is running. We therefore open the name list and we face that it is not over, because we have to choose which is the best parameterization set for our domain. We know that sometimes or often the choice may be critical to obtain the correct representation of the fields we are analyzing. And the truth is that we have much more than one choice to make. Sometimes it's very complicated and challenging. So this is the list of the most important parameterizations we used in the model. So we have the land surface parameterization, the radiation scheme, the boundary layer, moisture, convection, and the cloud fraction. So I will not go through the formulation of the land surface and the radiation schemes, as they are internally coupled models for which one can find the descriptions in the references that I wrote here. And I will therefore start with the boundary layer schemes. So these are used to parameterize the unresolved turbulent vertical fluxes of heat, momentum, and constituents such as the moisture within the planetary boundary layer and throughout the atmosphere. We know that turbulent fluxes cause mixing of heat, moisture, and momentum. To describe this, there are two different types of schemes. The local schemes, where the turbulent mixing is estimated at each point in the vertical from the local gradients of wind and potential temperature. The assumption that fluxes depend solely on local values and gradients of basic model variables may fail in the unstable boundary layer, for example, under convective conditions, when turbulent fluxes are dominated by large eddies in which the transport covers longer distances. Non-local schemes are used for conditions when the largest transporting eddies may have a similar size as the boundary layer height itself. They determine an eddy diffusivity profile based on a diagnosed boundary layer height and a turbulent velocity scale. They also incorporate non-local, so vertical transport effects for heat and moisture. In Regcm, we have two different options for the boundary layer. Setting IBL type equal to 1, we activate the Holtzlag scheme, which has been a part of the Regcm model since the Regcm2, and it is a non-local scheme. In the Holtzlag scheme, the origin of turbulent mixing is the surface heating due to incoming solar radiation and the related static instability. The boundary layer height is diagnostically computed from wind components, from the virtual potential temperature, and the critical bulk Richardson number. The diffusion coefficient at every height in the model is an empirical function of both surface condition and fractional height within the boundary layer. Because the diffusivity is only a function of surface condition, this diffusion parameterization implicitly assumes that the turbulence within the boundary layer is generated entirely from the surface. The drawback of this approach is that the Holtzlag model only considers surface-related sources of turbulence. It entirely neglects cloud-top radiative cooling as a source of turbulence. Without this source of turbulence, the occurrence of boundary layer clouds over the ocean will be limited to areas and times where surface-based convection or mechanical mixing is strong enough to transport moisture from the surface above the lifting condensation level. The boundary layer scheme is activated when we set IBL type equal to 2. It is the University of Washington scheme, and it was originally implemented to allow Regcm to simulate the stratocumulus and coastal fog. In the figure, at the top we have the low altitude cloud fraction from the satellite, and in the bottom left we have the net cloud radiative forcing. So we see that in negative blue and violet colors indicate areas where the net radiative forcing is negative, and these are actually the areas where stratocumulus form. Stratocumulus clouds are very important because of their large cloud fractions and because of their impact on the atmospheric radiation budget. According to Bonny and Dufresne in 2005, they are the main responsible for the model differences in representing the cloud feedbacks. So this scheme was implemented probably to simulate these kind of clouds. And in contrast to the host-lag model, the model prognostically determines the turbulent kinetic energy, and it uses the turbulent kinetic energy to define the diffusivities. So at each model time step, the UW model does the following. It determines the boundary layer height, it calculates the surface TKE, it predicts the change in turbulent kinetic energy due to the boundary layer processes, it determines the diffusivities at each height, and predicts the change in each prognostic quantity due to vertical convergence of turbulence fluxes. This model accounts for the production of turbulence by cloud top radiative cooling, which leads to the formation of stratocumulus clouds. And for the formation of these clouds, it needs to include the microphysics parameterization. So these are the two boundary layer schemes. Now we can analyze the moisture scheme, which is the parameterization that resolves the large-scale precipitation. In Regcm, we have three options. So setting IPPTLS to 1, we activate the SubX scheme, which is the oldest scheme developed in 2000 by Pal et al. And it deals with one prognostic variable for cloud water. It divides ice and liquid according to the temperature, and it has one diagnostic variable for rain, which falls out instantaneously. At the bottom we see the liquid water fraction with colored dots representing data from different level pressures. So in red we have in red we have the surface, and in blue we have the top of the troposphere. So this quantity, this liquid water fraction, represents the partition between liquid and ice in mixed phase clouds. For this scheme, the liquid water fraction is a function of temperature. Below -30 degrees, the clouds are completely glaciated, while above -10, the clouds are made of only liquid. Moreover, for each height, clouds are characterized by only one liquid fraction for each temperature. The other scheme, setting IPPTLS to 2, is we activate the Nogherotto-Tompkins scheme, or Noto to his friends. The scheme is built upon the CMWF integrated forecast system and solves five prognostic equations for five prognostic variables, which are the water vapor, cloud ice, snow, rain, and cloud liquid. The numerics are implicit and therefore allow the use of longer time steps. It is flexible, as it is possible to insert easily new variables if one wants to do it in the future. And it checks at the end of each time step the conservation of water and energy. So let's now have a look at the liquid cloud fraction. So in the middle we see the liquid cloud fraction generated by the Noto scheme. They look realistic when compared with observations at the right. compared to SABEX scheme, which was setting automatically to 0 all the liquid water below minus 30 degrees. This scheme allows the existence of liquid water at temperatures lower than that threshold. At each temperature, with this scheme coexists a wider variability of clouds. For example, at minus 15, the clouds can vary from all ice to all water through varying fraction of supercooled liquid water. In this scheme, parameters to play with are the autoconversion schemes, which are the parameterizations that produce the rain from the cloud liquid. The scheme has 4 different autoconversion schemes. The Kessler is the same used in SABEX. It's a very simple parameterization that assumes a critical value for the liquid that represents a threshold for the occurrence of the autoconversion. For cloud liquid water content greater than this critical value, the autoconversion rate is linearly related to the liquid, while for values below, no autoconversion occurs, of course. The other 3 schemes use an alternative approach without discontinuities by they include a smoother threshold function. And also for the ice autoconversion, the scheme uses an exponential approach by Sundquist in 1989 with a specific coefficient for ice particles depending on temperature. Now, setting IPPTLS to 3, we activate the warp single moment 5 class microphysics scheme. This scheme treats separately ice and water saturation processes, assuming water hydrometeors for temperatures above freezing and cloud ice and snow below the freezing level. It accounts for supercool water and a gradual melting of snow below the melting layer. The scheme includes the size distribution of ice particles and, as a major novelty, the definition of the number of ice crystals based on ice mass content rather than temperature. It has only one autoconversion scheme, which is the Kessler one, the same of SABEX, for both rain and ice. Now, convection schemes. So, the moist convection, we know that it alters the environment in 2 different ways. There is the deep convection, which is associated with strong updraft and precipitation, and it acts to warm and dry the environment. And then there is a shallow convection that produces no net warming, but it is important for the radiative budget. We also know that a convection scheme has to predict the convective precipitation, change the vertical stability, generate and redistribute the heat, remove and redistribute the moisture, and to form clouds. In Regcm, we have 5 different schemes for the convection. The parameter you need to set in the name list is this ICAP. Okay, here I outlined a table with the 5 different convection schemes in Regcm. Be aware that the QO scheme is not available for Moloch. And here you can see in the first column, we have in the first row, we have the trigger conditions. So for each scheme, what is the situation that activates the convection? And then you can see the different assumptions made by the scheme. So I will not go into the details, but you have the slides so you can further explore the table whenever you want. If we had to summarize the schemes, we could say that QO, for example, initiates the convective activity when the moisture convergence exceeds a threshold and the column is thus convectively unstable. A fraction of the moisture convergence is then converted into rainfall while the rest does not condensate. It just has one updraft. The gray scheme considers convective clouds as made of two steady-state circulation. It has one updraft and one downdraft with no mixing with the environment occurring along the column but only at the top and at the bottom. The Mitter-Manuel scheme considers the effect of mixing but assumes it is highly episodic and inhomogeneous. Convection activates when the level of neutral buoyancy is higher than the cloud base level. Within the two levels, air is lifted and condenses, forming precipitation. Air is allowed to mix with the air from the environment, and the mixing entrainment and detrainment rates are function of the vertical gradients of buoyancy in the clouds. With respect to the other scheme, the Mitter-Manuel scheme offers a more physical representation of convection, as it includes a formulation of the autoconversion of cloud water into precipitation inside the clouds. The Tiedtke scheme considers both cumulus scale updraft and downdraft. It has 3 updrafts for the penetrative, shallow, and mid-level convection, and 1 downdraft. And it is activated when the lifted parcel reaches a lifting condensation level. In this case, the penetrative or the shallow convection is activated, otherwise the mid-level convection is activated. And then we have the Cambridge scheme, in which the convection is controlled by large-scale velocity in the vertical direction, and it has also has a convective updraft and downdraft, and also includes the compensating subsidence. Be aware that if you want to use resolutions finer than 4 kilometers, you need to set I cap equal to 0, because automatically in this way the convection permitting mode is activated. Now, the cloud fraction scheme. So this scheme is the parameterization that decides or is able to formulate what portion of the grid contains a cloud. So the model has 2 schemes. The first one is the sub-X, where the cloud fraction is calculated diagnostically from the relative humidity with this equation, where RH mean is the relative humidity threshold at which the cloud begins to form, and RH max is the relative humidity where the cloud reaches unity. As mentioned before, large-scale relative humidity is the most frequent predictor for determining the cloud amount in existing diagnostic parameterizations. However, this scheme allows situations where one could have cloud liquid without having any cloud. So, setting ICLD frac to 1, we activate the Xu and Randall scheme. This scheme was developed by Xu and Randall. They proposed a semi-empirical cloudiness parameterization that uses the large-scale relative humidity, but also considers the large-scale average condensate, which is the cloud water and the cloud ice, as the primary predictor. So in the equation, we don't have anymore only the relative humidity, but we also have QL, which represents how much liquid and ice we have within the grid box. This figure is taken from their paper and shows the correlation between the cloud cover and the relative humidity at the top, and the cloud cover and the total condensate, ice and water, at the bottom. So their conclusion was that the cloud amount is poorly predicted by the large-scale relative humidity, but is very well predicted by the domain average cloud-water mixing ratio. So I hope that I have clarified a little bit how to play with Regcm parameterization, and I wish you to find the right path. But overall, to have a lot of fun this week with your experiment.